Welcome back. Awesome. I think this is we kind of I kind of feel like we've reached almost like the crescendo almost of the course now. If we think back to where we started, we started talking about action potentials and information and the idea of cortical columns switching on and off and generating information and connecting to each other and receptors and intracellular signaling pathways, and by building up these ideas gradually and slowly and deliberately carefully, we've reached the point where we can read a passage from the Doors of Perception, the most important, perhaps the greatest trip report ever written, and say, I understand how that works. I understand what's going on in Aldous Huxley's brain when he's writing that, when he's having that wonderfully kind of mystical experience, looking at this vase of flowers, and it doesn't take away from the magic of the experience, but it adds to it in a way, and that actually, we're able to understand it, to understand why that's happening, in terms of really quite simple ideas that we've kind of built up very, very slowly. So but we're not finished there, as I said last time. We can do a little bit more. So let's just develop this idea further. Let's now think about, so the last thing we discussed was that when the world model starts to be disrupted and information starts flowing out of these normally well-demarcated cortical column networks, the brain loses its ability to predict the patterns of sensory information. Now, what does the brain normally do under normal circumstances when it fails to predict sensory information? The brain is always trying to successfully predict the next pattern of sensory information. And it's basically trying to keep those error signals down, right? That's what it's always trying to do, reduce the error signals. And it does that by updating its model. And we did look at this in, I think, probably Unit 4. We looked at this idea that the brain, using the error signals, once these error signals reach the higher levels of the cortex, the brain uses them to essentially update its model in order to reduce them. So let's have a look at how we imagine this. So this is our normal, regular, hierarchical, top-down information flow model. We're trying to predict this sensory information, and we fail. We get this bottom-up prediction error, which flows upwards, bottom-up, to the high levels of the cortical hierarchy. And what does the brain do then? Well, it attempts to reduce those error signals. So this was our original model, the model that failed, as we just saw, and generated these error signals. So what does the brain do? It updates its model. It updates its model in an attempt to reduce those error signals. So with the updated model, so this is the new model, this is the updated model. What happens? It's successful. So the prediction error has been successfully quashed. But what happens when a psychedelic is in the brain? So we saw that the world model is disrupted. The brain fails to predict the sensory information. You get an increase in information, thus, in the form of error signals flowing upwards to the high levels of the cortical hierarchy. And the brain then, what does it do? It tries to correct the errors. It tries to update its model. But it fails. It cannot form a stable, coherent, precise, well-defined model. And so it keeps trying. It keeps updating its model. It keeps updating its model in an attempt to find the best explanation for the sensory data. And that is, of course, the model that results in the lowest amount, the smallest number of prediction errors. But it fails at doing that. And so what happens to your world model? Not only does your world model change and become disrupted and kind of is sort of dismantled by the psychedelic, but the brain, as it continuously is trying to update your world model, the world becomes unstable. It's changing. You look around, you see something, and you think, "What is that?" And your brain kind of is trying to find the best explanation, but it can't. So you might see somebody's face kind of transform into the next best guess that your brain can come up with, which might be the face of a lion or a monster or a beautiful angel or whatever. And this is what is happening. Your brain is constantly trying to update its model, but it's always failing, and so the world becomes much more fluid and much more unstable as your brain is shifting from model to model, just trying to reduce that bloody prediction error. Now, there's a good example from Sasha Shulgin's book, Pikal, where he actually describes this effect, and so why not read it to you. So he says, "I sat there on the seat of the car looking down at the ground, and the earth became a mosaic of beautiful stones which had been placed in an intricate design, which soon all began to move in a serpentine manner." What has happened here? The brain updated its model, which included this mosaic of beautiful stones, but it was still getting all of these error signals. So what did it do? It thought it kind of updated the model and settled on, kind of a serpentine structure, something like a snake. What happens next? Then I became aware that I was looking at the skin of a beautiful snake. All the ground around me was this same huge creature, and we were all standing on the back of this gigantic and beautiful reptile. So this is why, under the influence of psychedelic drugs, particularly if you have a fairly decent dose, you can indeed start to, people would refer to these as hallucinations or illusions or whatever, but these are alternative models, alternative explanations for the sensory information that your brain is generating in an attempt to reduce all these errors, reduce all this information that's flooding the brain in the form of these error signals. And since it fails, it keeps attempting it, and this is why the world becomes much more unstable and much more fluid. Okay, so that's kind of three major kind of sensory effects now that we've been able to explain. The initial disruption of the world model, the increase in the flow of information entering the brain in the form of error signals as a result of that, and then the consequence that the brain continuously is attempting to update its model in order to try and reduce those error signals. Okay, so let's go one step further. Now, this is a little bit different, but again, it's based on again the principles that we've been developing over the last few units, and this is particularly based upon what we discussed in Unit 2. So in Unit 2 was the very short unit on information, and I said to you, mark my words, this is going to be important. This idea of information and the idea that information is generated when a system selects between a finite number of distinct states. And we saw that the more states that a system can select from, the more states available to the system, when it selects one of those states, it generates more information, which is why, for example, when you roll a dice, for example, and it lands on a 6, that contains more information than when you flip a coin, which only selects between two states. And of course, the brain is selecting between a vast number of states. But it's not an infinite number of states. So let's think about, how much information is there in your world model? So look around you now and think, okay, how much information is there in the world model that I'm currently experiencing? Well, you can't give that obviously it's a lot of information, right? It's a vast amount of information. But ultimately, it's determined by the number of states, a number of possible states of all of your cortical columns that are ruled out when the brain selects the current state, the moment now, the world you're experiencing at this very moment. So let's try and quantify this a little bit. So we saw in again, back in Unit 2, this idea that, so I'm showing this here, this is an old kind of image. So here we have this kind of, this four-state system that has, state 1 all the way through to state 4, and this generates a certain amount of information when it selects between one of those states, and that you can constrain the number of states by connecting these individual units, and thus not allowing other kind of certain states, other particular. You're not allowing these states, basically. So these states are no longer possible because you have connected these units, and basically means that when this is blue, it forces this one to be blue. When this one is yellow, it forces this one to be yellow, and vice versa. So you've reduced a 4-state system to a 2-state system. You've constrained the number of states, and you've reduced the amount of information that this system can generate. And we kind of applied this simple principle to cortical columns. By connecting cortical columns together, you sculpt the possible states of the entire system. You sculpt the possible states of all of these cortical columns that make up your cortex. So this is what this is all about. This sculpting of your connectivity is about constraining. It's about making certain states more likely than others, because information, as we said, will tend to flow between columns that are connected to each other. So you're kind of reducing the number of possible states of the cortex over time. Now, we kind of looked at the development of your world model over time. I think that was in maybe Unit 4 or 3, but I forget. But anyway, and if we think about a set of cortical columns that are completely unconnected, and then I ask you the question: does this set of cortical columns, or can this set of cortical columns generate more or less information than this set of cortical columns? I'll give you a few moments to think about that, but you should answer that the independent set of cortical columns, this set of cortical columns here, can generate more information simply because there are more states available to it, because basically every possible arrangement, every possible pattern of activation of these columns is equally possible, because there's no influence of one column upon the other. However, when you connect these columns in a particular pattern of connectivity, you constrain the possible states, which means that when the cortical column selects a particular state, such as this state, it's selecting from a smaller number of states, and so it's generating less information. So we can see then that as the world model, your pattern of connectivity develops, the number of available states goes down. Your brain is sculpting the possible states. And so that also means that the information that can be generated by these cortical columns also goes down. Now, that's not a bad thing. It's not a bad thing that the brain is generating less information as it develops these patterns of connectivity. The brain is trying to develop a functional model of reality, and it doesn't necessarily pay to have too many states available to it, because then it can become kind of disorganized and difficult to manage. So this is a natural process where you're reducing the number of states over time by sculpting this pattern of cortical connectivity. But what then happens when you introduce a psychedelic drug? So you should know now, right? Let's say, LSD or something enters the brain, right? What's happening? Well, we're essentially, as we've discussed at great length now, you're essentially overriding all of this connectivity, and you're almost kind of pushing the brain back in this direction towards this kind of unconnected state, where you get in this democratization of cortical column connectivity, which means there's a greater number of states available to the brain in the presence of a psychedelic drug. So, when a psychedelic drug enters the brain, it increases the number of possible states, of the possible patterns of activation of all of these cortical columns. And that means when the brain selects one of those states, that state contains more information. So what that means is that under the influence of a psychedelic drug, every moment when your cortex selects a particular state, that state contains more information. Every moment contains more information. Your world becomes richer, it becomes filled with information. Not only is it a fluid and unstable, constantly changing world, and a world that's receiving more information from the environment because of the loss of this filtering mechanism that we discussed in the last video, but also every moment is richer because it's filled with more information. Wow. So I think that kind of just about completes, in fact, yes, it does. That just about completes our initial exploration of the effect of psychedelic drugs on the brain. We've come from action potentials and cortical columns to an understanding now of some of the major perceptual effects of psychedelic drugs. We're not done yet, but we have come a long way. We now understand why, when you take a psychedelic drug, initially your world starts to change. It starts to become, it starts to fragment. It starts to become unstable. It starts to become more fluid. You become more sensitive. Colors seem brighter. Objects seem to change their identity from moment to moment. The world just seems new and fascinating and magical and filled with significance and filled with information. And all of that we can explain quite simply, really, using the principles and ideas and concepts that we have developed over the last few units. Amazing stuff. So in the next video, we're actually going to turn our attention inwards a little bit. So far we've focused entirely upon the world outside, or the model of the environment. Of course, we've always been focused on the inside and the brain itself, but we've been pointed in the direction of the environment, and thinking about the change in your world model, the model of the environment. In the next video, we'll start thinking about what happens to the model of yourself, because that's also a model constructed by your brain. How is that changed under the influence of psychedelics? Well, we'll see in the next video, so see you then.